Hello everyone, I'm Zuhair and I'm here with my teammates.
I'm Seamus.
I'm Leander.
Together we have been working on an exciting project for our fluid mechanics class. Our topic is hydrostatic levitation. Hydrostatic levitation refers to the phenomenon where an object is held in a place by fluid pressure. In our case, air pressure from a hairdryer. This experiment is a fun and simple way to explore the principles of fluid dynamics, including airflow and pressure distribution. In our setup, we use a hairdryer and a ping pong ball to observe how air velocity and angles influence the levitation of the ball. We discovered that on low settings, the ball rotates and juggles close to the hairdryer. On high settings, it travels higher up to about 2 inches when vertical. However, tilting the hairdryer at a 45-degree angle gave the most dramatic result, with the ball reaching its highest distance of around 5 inches. Beyond that angle, the ball can no longer stay suspended and falls off. This experiment highlights how the interaction of fluid forces can maintain equilibrium, demonstrating key principles of hydrostatic pressure and stability. Now let's dive into the experiment demonstration.
Let's begin with the hairdryer set to low power. Notice how the ball stays suspended but close to the nozzle. It rotates and wobbles slightly, which shows how the airflow is working to balance the ball using low pressure and gravity. Now, we'll increase the hairdryer to high power. Here, the ball rises higher, about 2 inches above the nozzle. This is because the stronger airflow increases the upward force, countering gravity more effectively. When we tilt the hairdryer to about a 45-degree angle, the ball reaches its highest point, roughly 5 inches. The airflow remains strong enough to stabilize the ball in this tilted position. The interaction between gravity, airflow, and pressure keeps the ball suspended. But when we tilt further beyond 45 degrees, the ball falls off. At this point, gravity overpowers the stabilizing force of the airflow, causing the ball to lose balance. This experiment demonstrates how fluid forces interact, showing us how angle, pressure, and gravity all play a role in hydrostatic levitation.
The behavior of the ping pong ball can be explained using the pressure form of Bernoulli's equation, where P is the pressure of the fluid, rho is the density of the fluid, V is the velocity of the fluid, G is gravity, and H is the height of the fluid, which is all equal to a constant amount of energy per unit volume. Because there is very little change in the fluid's height and density in comparison to its velocity and pressure, this term becomes negligible, leaving us only with the velocity and pressure terms. So we now know if velocity decreases, in order for this to stay constant, pressure must be increasing. And vice versa, if pressure is decreasing, we know velocity must be increasing. When the hairdryer blows air, it increases its velocity, creating an area of lower pressure within the airstream. But when the air comes in contact with the bottom of the ball, its velocity must decrease due to friction, creating an area of higher pressure underneath the ball compared to the rest of the airstream. This pressure difference between the bottom and top of the ball counteracts the force of the ball's weight. If a horizontal force is applied to the ball, the airflow of the side that it's pushed into will have its velocity decrease, creating an area of high pressure. On the opposite side of the airstream, more area is freed up for the flow of the air, increasing the net velocity of the fluid on that side of the airstream, which creates an area of even lower pressure than before. The combination of the increased pressure on one side of the ball and even further decrease in pressure from before on the other side of the ball means the ball will resist being pushed horizontally out of the center of the streamline until pressure on both sides of the ball comes to an equilibrium. When the hairdryer blows the ball from an angle rather than directly underneath it, it can remain levitating. This is due to a similar reasoning as the previous example, but in this case the weight of the ball acts as the applied force. The weight of the ball pushes the ball down on the bottom of the streamline. Friction between the ball and air decreases the velocity and creates an area of high pressure underneath the ball. The force of gravity has relatively little effect of the air on top of the ball, allowing the velocity to remain higher than the bottom of the ball and the pressure lower. The pressure difference between the bottom of the ball and top of the ball allows it to counteract the force of the ball's weight. The horizontal component of the velocity of the fluid creates higher pressure on the side of the ball closer to the hairdryer and lower pressure on the opposite side of the ball, in the same way as the previous examples, except there is no force of gravity in the opposite direction to balance it out. The reason the ball is not horizontally ejected from the airstream is because the velocity of the air constantly decreases the further it travels from the nozzle, meaning pressure increases further from the nozzle. At the right point, the pressure difference caused by the horizontal component of the velocity is not enough to overcome the pressure of the slower moving air in front of it, balancing the forces on the ball. The reason the ball increases its distance from the hairdryer as the angle of the hairdryer is increased is because this transfers more of the pressure difference to act horizontally on the ball rather than vertically. But at the same time, this means that the pressure difference that acts vertically and supports the ball's weight is decreased. This means the ball's distance from the hairdryer will increase as the tilting of the hairdryer increases until there's not enough of a pressure difference between the top and bottom of the ball to support its own weight. Or if you have a strong enough hairdryer, once there's enough of a pressure difference acting horizontally on the ball as you tilt the hairdryer, it can overcome the higher pressure in front of the ball before the weight of the ball overcomes the vertical pressure difference acting on the ball. This results in the ball being ejected out of the end of the airstream. Bernoulli's equation was able to give us a simplified explanation for why the ball behaved the way it did in the airstream. Similar concepts using pressure differences are used in tons of different kinds of engineering, from moving water through a pipe to building and flying an aircraft. So obviously these are very important topics to understand. I hope you learned something from this video.